fashion, okay, but it's not clear. And can it is puddles, but what is the orientation of the spins? It's just the orientation of the spins. So the spin wave direction, what is it that you're thinking? So in that small puddle, so these puddles are actually quite big, they will have some thousands of mu b. And then what is the orientation of these spins? And can I tune this magnetic property with gate voltage as we can tune the electrical and mechanical properties? And that is one of the most interesting things. I will not talk on this, but we have seen that you can actually tune the magnetic properties using this gate voltage. It's probably the only material where you can do that. Coming to superconductivity, superconductivity was seen as a function of gate voltage. So this is at minus 100 volt, the system is an insulator. As I keep electron doping the system, it goes to a superconducting transition temperature, and the transition temperature is typically very low, around 100 to 300 millikelvin. And just like the height is in superconductors, if you plot the superconducting transition temperature as a function of the gate voltage or the number density, you get a nice dome like peak where there is a maxima at a certain given number density. Okay. On either side of it, the superconducting transition temperature begins to fall. You can look at, of course, DIDV, you see a pseudo gap. The pseudo gap's temperature is, at least in this low doping region, is much higher than the transition temperature, and there is some similarities between these high Tc copper oxides and the lanthanum aluminate, which are both plotted together. So this is a phase diagram of the high Tc, and this is that of the STO. Of course, the energy scales and number scales in the LAO, STO, the oxide system is much smaller, but still it's a much simpler system to study, and that's what got us excited and interested in this material. So now coming finally to our device. This is how our device looks like. It's a schematic. You have, this is the STO, the blue is the LAO, and this red here represents the two-dimensional electron gas at the interface. And you can deposit electrical contact pads on top in any configuration you want. In this example, it's a van der Pol, but you can make it into a Hall bar, you can etch it into a Hall bar geometry, you can make it into one-dimensional nanowire, and we have done all this. And in the bottom, you deposit a gold pad which acts as a global backgate, okay, which controls the total number density of this charge carrier into the system. Now the beauty, this is very thick, along 1 millimeter. The reason it can work as an FET is that strontium titanate is a quantum paraelectric. Okay. The dielectric constant of the commonly used dielectrics which we use, for example, like silicon dioxide, will be 4. At low temperatures, the dielectric constant of strontium titanate is around 25,000. Okay. So you can imagine, even if this thickness is large, the capacitance is still enormously high, and by applying a moderate back voltage, you can induce carriers of the order of 10 power 13 or 10 power 14 into the system, which we cannot do in conventional FET systems. So here is first the simple measurements showing the resistance as a function of gate voltage. As I apply gate voltage, the resistance falls monotonically, showing that it's an electron doped system, and the mobility begins to, and mobility increases significantly with increasing gate voltage, which shows you that the main limitations in the mobility comes from number density fluctuations, which I am just screening out by increasing the number of carriers. And then we start measuring the resistance as a function of temperatures at zero magnetic field. So this is at low negative gate voltage where my carrier density is very low. I increase the gate voltage and I can have a superconductivity in the system, which is Tc around 150 millikelvin, and you can just sweep the entire gate voltage range in the middle and map out the phase diagram. Now how do I know it's a 2D superconductor? Well, there are two ways you can do it, at least in this system. You can take this resistivity and fit it to this two-dimensional equation, and that gives you a Tc of around Kosteles-Thouless transition temperature of around 117 millikelvin. The second thing you can do is you can measure the current voltage characteristics of the system, and in this regime below the Kosteles-Thouless transition temperature or close to it, V goes as I to the power gamma, where gamma is a function of temperature, and this is a plot, sorry, this should be gamma. This is a plot of gamma as a function of temperature, and the temperature at which gamma becomes 3 is by definition the Kosteles-Thouless transition temperature. And using this definition, we can get TBKT to around 118 millikelvin. So within experimental errors at zero gate voltage, my transition temperature is around 120 millikelvin, let's say that. So now that we have got the transition temperature, we established it's a 2D material, we start measuring the system. And here is the entire phase diagram and this is what I have plotted here in this color plot, where this is the temperature, this is gate voltage, and this blue region is a superconducting region. Okay. Now, from now on, all the measurements, all the data that I will be speaking about were taken at this temperature 250 millikelvin, which is at least 120 millikelvin above the superconducting transition temperature. Okay. So, we will be sitting at this temperature and we will be sweeping the gate voltage and we will be measuring the magnetoresistance at each point along this dotted line. Okay. Please bear in mind that I am sitting at the temperature which is much higher than the superconducting transition temperature. So, we first start off at this end, where of course, I do not have any superconductivity and I start sweeping the magnetic field. I do the magnetoresistance. So, I see that the magnetoresistance is negative, it is hysteretic, and it is symmetric in magnetic field. And this is a clear signature that I have ferromagnetism at negative gate voltages, and that is what people have seen. When the carrier density in the system is very small, I have ferromagnetism in the system. So, in this region where I do not have superconductivity, I have evidence of ferromagnetism. I can now, and this is the hysteresis loop, you can see that the area of the hysteresis goes down as I increase the gate voltage, and beyond a certain number density it completely vanishes. The hysteresis in MR goes away. Now, we go to the other extreme, the high, this one, at this point, I will come to it. Can I explain that little? Yes. So, that arises just because of the hysteresis and finite relaxation time of the system. I will come to a detailed answer. Now, we sit at the other end where I have the largest carrier density and I again do the magnetoresistance in this region. What I see is that the magnetoresistance is positive. Remember, at low number densities the magnetoresistance was negative. Here the magnetoresistance is slightly positive, and something interesting happens in this system. So, here I was going from a 0 magnetic field, I sweep it out to 8 Tesla magnetic field, and then I start decreasing the magnetic field very, very rapidly. What we see is that as we come close to around 10 millitesla, the resistance of the system becomes immeasurably small. So, it is 0 to within my measurement resolution. It is smaller than few tenths of a nano ohm. Okay. Remember, I am sitting at temperatures which are at least 100 millikelvin above my superconducting transition temperature, and I do not expect any superconductivity in this regime. But what we see here, at 0 magnetic field the system was normal, I go to a high magnetic field, I start sweeping down the magnetic field. As I am close to 0 field, the resistance suddenly drops to 0, and it is symmetric in magnetic field. This is what we call a transient superconducting state. It is called transient because if I stop at 0 magnetic field, I see that the resistance relaxes back to the normal value with a time scale of around 20 to 30 seconds. Okay. So, I have a finite resistance, I go to a high magnetic field, I have a slight positive magnetic resistance, I start coming back very fast at the rate of around 1 Tesla per second. Okay. Okay. Sorry, 1 Tesla per minute, that was too fast for me. 1 Tesla per minute, I come to 0 Tesla and the resistance goes to 0. I switch off the magnetic field and do nothing, I just wait. And as I wait, I see that the resistance relaxes back to its original value, what it had. It has an overshoot and then it just saturates. Okay. So, this times constant was of the order of tenths of seconds. Okay. So, just to see if this is a real drop, we just measure it very fast using DAC cards, and we found that really it drops, and the drop starts from around few tenths of millitesla. Below that it just drops by orders of magnitude and becomes immeasurably small for us. So, now then, as soon as you see something like this, the first question you ask itself, it must be an artifact, right. So, the first artifact which comes to your mind is that I have a system where I am changing the magnetic field very fast. Whenever I change a magnetic field very fast, I can have adiabatic demagnetization, which can lead to cooling of the system. So, we went back, we calculated, and this is a ferromagnetic system. So, I have spins which are aligned in a magnetic field, I sweep down the magnetic field very fast, the spins de-align, and that can give to me an adiabatic cooling, just like in the adiabatic DR you have here in Ramke's lab. Now, we went back and calculated the effect, how much it should give us, and we calculated that this can give us a cooling of at most a millikelvin or less. I needed 100 millikelvin. So, this was obviously not the reason. So, then we went back, okay, we know that reduced strontium titanate has very similar superconducting properties as this LeO-STO heterostructure, and we did these measurements. We measured increasing field, decreasing field, they just fell on top of each other, there was no transient superconductivity. We went to another control system, which was lanthanum titanate, strontium titanate. The system which we were working now till now was lanthanum aluminate, strontium titanate, which has signatures of ferromagnetism and superconductivity. Lanthanum aluminate, lanthanum strontium titanate, you can make the same heterostructure, you will get similar superconductivity, but there is no signature of ferromagnetism in this system. So, in this system I do not see any transient superconductivity. So, in both my control systems I do not see any transient superconductivity. We went further ahead and we did these measurements in a parallel field. So, we can rotate the sample and we did it at different angles with respect to the magnetic the sample with respect to the magnetic field, and we saw that whenever the sample is aligned parallel to the sample to the magnetic field, we do not see this effect. So, this obviously is an orbital effect.
Just a technical question.
Yeah.
You are using a superconducting magnet. What is the resonant field of the superconducting magnet?
Okay, it's a very good point. So, we had warmed it up, it's because of the dry DR, that is also something which we checked because the refrigerator told us to do. We warmed up the system to room temperature, and in the first one we saw it. So, there was no trap, 0 to 8 and coming back.
Yeah, but when you have 8 and come back, there is a resonant.
Yeah, that will have a lot of milliteslas.
So, the reason I am asking is that you see this strange time dependence.
Mm-hmm.
Now, when you sweep very fast, you might have trapped flux in your superconducting magnet that will slowly relax and
That's right. That's right. That's right. Yes. Yes. Might be. So, that relaxation might be because of that, because there is a small magnetic field which is slowly relaxing. Okay. So, then of course, we did these measurements under with different DC currents to get the critical current, and we got the critical current to be around 2 microamp, which is what we get the exact critical current we get at temperatures below the critical temperature. So, the critical current, the HC2, everything seemed to match of this transient superconducting state and the parent superconducting state. So, now we started seeing, okay, what is the effect of the sweep rates? For example, we did this measurement when you swept the magnetic field at 0.1 Tesla per minute, we got a small dip, nothing else. At 0.2 Tesla per minute, the dip increases, 0.5 Tesla per minute, the dip is much more, but it never goes to 0. So, when we go to 1 Tesla per minute, we see that it identically goes to 0, becomes immeasurably small. So, there is something to do with the rate of sweep of the magnetic field, the rate at which the magnetic field is changing, that much we figured out. Okay. So, here is the magnetoresistance at our gate voltages. So, at large negative gate voltages, my magnetoresistance was negative. There is, as you can see, there is a hysteresis loop, and as I keep increasing the gate voltage, some kind of transition happens here at this point. The magnetoresistance goes from negative to slightly positive, and I start getting this transient superconducting state. So, there is a critical number density at which some kind of a transition is happening in the system. So, to understand that, we started measuring the number density. Now, we took the sample in a Hall bar and we measured the number density. Okay. We took the RXY, fitted it to a single electron model and extracted the number density. As expected, the number density kept increasing with gate voltage, but beyond a critical gate voltage where this transient superconducting state appears, the number density apparently begins to decrease, which is unphysical, it cannot happen. I have a gate voltage, the number density, I am pumping in electrons, the number density must increase, and we know what this artifact is, I will come to that. So,
what is the multiband transition?
Here, that is the multiband transition. So, now you can take the dielectric. So, as I told you, strontium titanate is a very strong, is a quantum paraelectric, which means its capacitance depends very strongly on the electric field. Okay. Capacitance is epsilon naught by d per unit area, but this epsilon naught epsilon r, this epsilon r is a very strong function of gate voltage. When you are normally doing a field effect transistor with SiO2, you do not have to care about it, because for silicon dioxide the gate dependence of the dielectric constant is negligible. For strontium titanate it is extremely strong, it can change by a few times. So, we took that into account and these dotted lines are the calculated number density and green is what I would expect. Until this point it matches very well, beyond that something else happens. So, what do we know till now? That as Pratap pointed out, this probably is the point where there is a multi-band transition happening. And this is known, it was seen before that there is a Lifshitz transition which happens beyond a certain number density, that the rho xy becomes nonlinear in B, and there are two kinds of carriers. Okay? So, at low carrier densities my chemical potential is here, all the transport is happening, all the carriers are only in this band. Okay? As I keep increasing my gate voltage and pump in more and more carriers into the system, at some point my chemical potential will reach here, and at this point I have a multi-band transport, and I cannot use the simple RH equal to 1 by NE to extract the number density. I will have to start using the multi-band transport equation. And so, here is our data. This is, as you can see, Rxy is linear in magnetic field at low number density, at low gate voltages, but it becomes very non-linear at high gate voltages. And then you can fit this equation with this multi-band model. You can extract, you find that there are two kinds of charge carriers. There is a high number density low mobility charge carrier, and there is a low number density high mobility charge carrier. Okay? And we know from previous experiments that it is these low number density but high mobility charge carriers which are responsible for superconductivity in the system, and these high number density low mobility charge carriers which are responsible for ferromagnetism in the system. So, although this system has both superconductivity and ferromagnetism, they occur in different bands. The electrons in the dxy bands, which have a lower mobility but a large number of electrons, they give me the ferromagnetism, while the electrons in the dyz band, which have a much higher mobility but a low number density is much lower, they give me the superconductivity. Okay. So, agree. So, yes. So, this is, as you pointed out, this is an empty band